Okay, so I think we are being recorded. So we are now ready to start the lecture. And today, as I promised, we will be talking about Aries stress function. So let me share the screen and then we can start with the lecture. So, okay, so now the screen has been shared and I believe you can see my slides. So what we will be talking about today is known as the Aries. So Aries stress function, and this has direct relation with whatever we discussed in the previous two lectures. So what we discussed in the previous two lectures, we discussed about plane stress condition, and we also discussed about plane strain condition. And if you remember, for both these cases, the things we discussed about are: first is the stress strain relation, which is also known as the constitutive relation, and we derived how stress is related to strain and how strain is related to stress. And then we talked about compatibility condition and equilibrium condition. We merged the compatibility condition with equilibrium condition and stress strain relation to arrive at the governing equation for plane stress condition and for plane strain condition. And if you remember, I'm going to consider that there is no body force, and under that assumption, we arrived at the equation that del 2 del x2 plus del 2 del y2 sigma x plus sigma y is equal to 0. And why is it 0? Because we are assuming that there is no body force. This will also be 0 if we assume that the body force is uniform. So there is no change in the body force with from point to point. So this equation, you get it for both plane stress and plane strain condition. So you get it for both plane stress and plane strain condition, right? So this equation will not change whether it is plane stress or plane strain. And then again, I told about that although the equation is same, the solution will be different. Why? Because the boundary condition can change from a plane stress problem to a plane strain problem. And also, once you have sigma x and sigma y, sigma z in case of, okay, there is one mistake. You should always write 2 index because it is a tensor. So once you have sigma xx and sigma yy, then for plane stress condition, you will directly substitute sigma zz to be equal to 0. Whereas for plane strain condition, sigma zz will be nu sigma xx plus sigma yy. Right? So the solution will not be the same, but the governing differential equation is the same. That is the bottom line. Also, we discussed about that stress strain relation that you see here is different for plane stress and plane strain condition. stress strain relation is different for plane stress and plane strain conditions, right? So they are not same. Don't confuse it. They are different. Only this thing is same. So only the governing equation is same, and that is also same, or that is only same when the body force is uniform or zero. So we will refer to this in today's lecture because Aries stress function is something very closely related to this equation. Okay, so we'll be referring it. So now, as I was saying, so what is Aries stress function? So the name itself says that it is a stress functional. So, so we are talking about Aries stress function. And from the name itself, you can probably guess that there was someone called Aries who proposed this thing, and whatever we are going to do with is a function of that will represent the stress. So that is true actually. But before we start working with Aries stress function, we need to know that this is only used in 2D cases. So you can use it for plane stress case, you can use it for plane strain case, or you can use it for purely 2D case where there is nothing in the third dimension. So that is ideal scenario, but you can use it for 2D cases. But even then, this method works better if you have traction boundary condition. So if you have traction boundary condition, this method is good. But let us say you have displacement boundary condition. In that case, this method is not so good, right? Not so good. It will still work, but it is not that good. Okay. Although the problem we will solve today, we will solve one problem today, at least partially. And for that problem, you will find that there is a displacement boundary actually, right? So these are the two conditions for which you can use Aries stress function. And what is Aries stress function? So it is a function phi that we define, and this phi is known as energy potential. Now, you may ask me that if phi is energy potential, why are we not calling it Aries potential function or Aries energy potential function? That is because using this phi, you can define the stresses. So that is why we call it Aries stress function. So there is a single energy potential, and using that potential, you can define all the stress components. Obviously, in the 2D case we are talking about. For 3D, Aries stress function is not used, right? Now, Aries stress function, if we go into the history, it was very popular when it was first proposed, because in those days we did not have computers, supercomputers, so you have to solve the problems analytically by hand, and for that Aries stress function is very good. But then time changed, computer came into picture, finite element method came into picture, and nowadays this method is kind of obsolete. No one uses it, but still this is somehow lays the foundation for finite element method, because you work with energy potential and all those things in finite element as well. So in that sense, this is still relevant. But when it comes to actual implementation, you will not see Aries stress function, right? So let us see what did we cover till now. So in this section, and this is only applicable for 2D static linear elasticity problem. And also what is not written here is this is only applicable for isotropic problem also. If you have an orthotropic problem, this will not work. So it has several limitations, but importance of a technique is always based on, I mean, you have to judge the importance of a technique based on the context in which it was developed. So this was developed at a time where there was no computer, orthotropic material was out of picture, so everything was analytical by pen and paper. And in that context, this method is very important. So yeah, that isotropic is also written here, as I was saying. And it can only be used also. So body force we will not be talking about, but this can also be used for body forces. But in that case, the body force should have a very special form. And this thing I already discussed that it only works if the traction on the boundary rather than some displacements. So this is something I already discussed. So this slide, I will go through this slide and then we will proceed with an example. So how Aries stress function is used. So we have this equation, and how we arrive at this equation I will show you in a little while. So on the left hand side you can see that it is a fourth order equation in phi, and then so this is known as Aries potential or a scalar function. This is a scalar function, and then we have a fourth order equation on the left hand side, and on the right hand side we have the body force terms. And by looking at it, I'm quite sure you can find the similarity with the governing equation for plane stress and plane strain condition. In both cases, on the right hand side, there was del B1, or I was writing del Bx by del x plus del By by del y. So that is something we have already derived. So let me first finish this one condition. So this term you can understand. And now you see when it is in a plane stress condition, this constant term will become 1 by 1 minus mu, and when it is in a plane strain condition, this will become 1 minus mu by 1 minus 2 nu. So this 1 minus 2 nu was also there in the expression of the stress strain relation. So there is a relation, and we will come to that relation in a little while. So for now, let us say we have this equation, and that is a fourth order equation. Let's assume only this part, and I will come back to that. Now, I said earlier that using Aries stress function, we define the stresses, and this is how it is defined. That second derivative of the potential with respect to y will give you sigma xx. Second derivative of phi with respect to x will give you the sigma yy, and take derivative once with respect to x and once with respect to y, that will give you tau xy, right? So you have the expression. So now let us see what happens here. So we are here, and let us go back to our governing differential equation. Governing differential equation for plane stress and plane strain condition. So we go back here, right? condition. So what is the governing differential equation? It is del 2 sigma xx del x2 plus del 2 sigma xx del y2 plus del 2 sigma yy del x2 plus del 2 sigma yy del y2 is equal to 0. So I'm not considering any body force. Now, by definition, we have sigma xx to be equal to minus, not minus, sorry, plus del 2 phi by del y2. We have sigma yy to be equal to del 2 phi by del x2, and then we have tau xy to be equal to minus, so there is a minus sign, then del 2 phi del x del y. So this is by definition of Aries stress function. So what I'm going to do is I'm going to take this sigma xx, sigma yy, tau xy, and I'm going to compute the above terms, and then I'm going to substitute it to see what we will get, right? That is the idea here. Remember that we also have another equation, that was the equilibrium equation, that we have to refer. So we will refer to that also. So in any case, let us see. So you take derivative of, so there is del 2 sigma xx, right? So take del 2 sigma xx del x2. If you do that, what do you get? So I'm talking about the first term. You will get del 2 phi by del x2 del y2, right? Let's talk about the second term, that is del 2 sigma xx by del y2. You go to here, take derivative twice with respect to y, and that will give you, okay, this is 4, right? So del 4 phi by, so what do we have here? By del y4. So these two terms we have done. Let us go to the third term. We have del 2 sigma yy del x2, and here is your sigma yy. So this will give you del 4 phi del x4, and the last term del 2 sigma yy del y2 will give you del 4 phi by del x2 del y2. So this is 1, this is 2, this is 3, and this is 4. So we take these 4 terms and substitute it into the governing equation A. And what do we get? So this space is enough. So the first term is this one. So first term will give me del 4 phi del x2 del y2. The second term will give me del 4 phi del y4, which is this one. The third term will give me del 4 phi del x4, which is this one. And the last term will give you del 4 phi del x2 del y2. So what I can do here is, let us see what we can do. Let me take the eraser. So there is one term here and it is repeated here. So let us remove the first term. And instead, what we will do is take the pen, add a 2 here, and that is equal to 0. So this is the equation, the governing differential equation in terms of the Aries potential, or which is we also call it energy potential. So this is the same equation that was shown here. If you take the right hand side to be 0, so this is actually the exact same equation that we derived in the previous lecture, and this is represented as this one. So nabla is derivative, so fourth derivative of phi, and that is how you represent it in the tensor notation or in the vector notation, right? Now, so what we are going to do, can you guess what we are going to do? It's actually simple. So we have this equation, which is del 4 phi del x4 plus twice del 4 phi del x2 del y2 plus del 4 phi del y4, and this is equal to 0. So now what we can do, I mean, how is this important? So what, I mean, if you have been given a problem and we will solve a problem, so what we will do is we will assume phi uh, as a function of, let us say, x and y, and then there will be some parameters which I am writing as theta. So this theta will be the unknown coefficient. So for example, if I write phi to be ax plus bx square plus cxq plus dy plus eyxy plus fyq. So if I write it like that, so in that case my theta, the parameters are a, b, c, d, e, f. And these parameters are unknown. So you don't know whether what you have assumed is correct or not. That is unknown. And these parameters are unknown. And somehow we want to compute these parameters. Parameters are to be computed. So this is a compressed way of writing um, phi or any as a function. This is a compressed way of writing any function, right? And you see here is a comma and here is a semicolon. So this semicolon indicates whatever is after the semicolon are parameters which we need to compute. So we assume this phi, and then what we do is, once you have this phi, we need to, I mean, we can find out sigma xx, which will be del 2 phi by del y2. We can find out sigma yy, which will be del 2 phi by del x2, and we can find out tau xy, which will be uh, del 2 phi by del x, del y, and there is a minus sign. So we will compute the stresses. So this will become the second step. What will be the third step? Use stress strain relation to compute to compute epsilon xx, epsilon yy, and gamma xy or epsilon xy, either of these, right? So the third step is use stress strain relation to compute epsilon. If you know stress, you know strain by using the constitutive relation. So we assumed phi, which is unknown. So there are some parameters which are unknown. Then we computed sigma again. So sigma will be in terms of the parameters. So for example, if I use this equation and if I compute del 2 phi del y2, what will I get? Del 2 phi del y2 is nothing but 6fy, right? When everything else will become 0, this is the only term that will remain after taking two derivatives. So you can see that this is also a function of this f. So we can say this is also a function of theta. I mean, this is also, you can think of it this to be function of a, b, c, d, and e, where they are multiplied by 0. Okay. So the second step is represent sigma xx in terms of the assumed phi. Step 3 is represent the strains in terms of sigma xx, sigma yy, and the other stress components. And these stress components are represented in terms of phi. So epsilons are also represented in terms of phi. So epsilon are also in terms of phi. And since we have parameterized phi, this means epsilon is in terms of theta. So if you know theta, you know phi, because x and y are the functional terms. So unknown phi means unknown theta. Known theta means known phi. So unknown phi implies unknown theta. And then if we know theta, if we know theta, this implies we know phi. And that implies we know stress, then we know strain, right? So in any case, so epsilon is represented in terms of phi. This is step 3. Step 4 is, so you have now your sigmas and epsilon and all those things. We are going to use epsilon. So compute displacements by integrating epsilon. So for example, we already know that epsilon xx is del u1 by del x. So this implies u1 is integration epsilon xx dx. So this is how we compute u1, u2, both the terms. So compute displacements by integrating epsilon. This is step 4. Step 5, and this is the final step. Satisfy boundary conditions to compute theta. And that's it. Once you know theta, you know u1, u2, epsilon xx, epsilon yy, sigma xx, sigma yy. Basically, everything becomes a known quantity to you, right? So that is the idea behind Aries stress function. So now what we will do is we are going to solve one problem, which is a cantilever problem, and that problem is shown here. So we now consider a cantilever beam, and this we are going to assume as our function, right? So let us start. So let me check first the coordinate axis. Okay, suppose we have a cantilever beam such as this, and my coordinate axis is at the center. This is my x direction, and if you go upwards, this is my y direction. So this length, or this width I should say, is 2c, which means from the center this is c and this is also c, right? And then if I draw it again, the cantilever, because I have shown the dimensions, so there is no space for what I want to do next. Okay, one more dimension I would like to show. This is L, length of the beam. And now at this surface, there is a shear force P that is acting. Now, I'm showing it like this because this is like the average shear force, a force acting. In the real scenario, this will not be like this. This will be something like this. So like a uniform shear acting. But in that case, the problem will become too complex for Aries stress function. So we don't consider this case. Instead, what we consider is our average shear, which is acting on this, and this is P. Remember the coordinate system? From center, this is the x direction, and this is the y direction. Okay. So now first step is, first is step 1, and step 1 is assume phi. We assume phi to be, say, a x y cube plus b xy. So this is what we assume. I mean, you can assume something else. It just have to satisfy certain conditions, like something should be at least of order more than 2, otherwise everything will become 0. But let us say we assume this to be our stress function. How will you know whether this is a correct stress function or not? You don't know. You assume based on your knowledge, your experience, and you work with it. If it does not work, you try something else. So it comes with experience, right? So in any case, we assume this to be our stress function or Aries potential. So where A, B are unknowns, where A, B are unknowns. So now step 2, we come to step 2, and step 2 is we compute stresses, right? Compute stresses, which means, so first I want to compute sigma xx, which is del 2 phi by del y2, and this will become 3, then 2 6, so 6 a x y, then we have sigma yy which is del 2 phi by del x2, which will become equal to 0. And then lastly, we have tau xy, which is minus del 2 phi del x del y, and this is equal to, so let us see, first let us take derivative with respect to x, so that will give us ax ayq, sorry, plus by, and this is, we have taken derivative with respect to x, so there should be derivative with respect to y, and then when you take derivative with respect to y, that becomes minus 3ay square plus b, right? So this is your tau xy. Now, what is the third step? Third step is to compute the strains. But at this stage, we don't compute the strains because we have one additional step. So boundary condition satisfaction was coming at the end. But in this case, we can actually satisfy certain boundary conditions. So it's better we satisfy the boundary conditions that we can satisfy, and then we will go to the stress condition, right? So step 3, we are changing it slightly from the general setting. Step 3 is we satisfy the boundary condition. Satisfy boundary conditions. So how many boundary conditions do you need? There is A and B, two unknowns. So we need two boundary conditions, right? So what are the two boundary conditions? You see at the top surface, so this one, and at the bottom surface, there is no shear component. Why is there no shear component? There is no shear component because when shear happens, when one surface slides over another surface. So since those are free end and there is nothing that can slide over it, the shear stresses at those points will be 0. So the first boundary condition is tau xy at y equal to plus minus c is equal to 0. So which implies b is equal to minus 3a c square. So you now have one relation, which is b is 3a c square, which means your tau xy is now, once you substitute b, you will get 3a will come outside, and then that is c square minus y square. And yes, all right. So this is the equation. This is your sigma yy. This is your tau xy after satisfying one boundary condition, right? Now what is the other boundary condition? So there is a traction kind of force, or I should say shear, that is acting. So that should be equal to the total shear that is acting. So basically, this is the average shear. So you will have a second boundary condition, which is integration of tau xy dy, and y will go from minus c to plus c. So this should be equal to this force, because that is the force that is acting on that surface. So we are, and why is this true? Because we are considering that the depth which is going inside your screen is 1. So this is actually dy times 1 that we are doing. So let us go to the next slide and we will continue with this thing. Just remember that this is 6axy and this is 3a c square minus y square, right? So remember these two things. So what do we have? We have sigma xx to be equal to 6a xy, tau xy to be equal to 3a c square minus y square. Then there is sigma yy, which is equal to 0, right? Correct. So now, with these three stress conditions, still A is unknown, and we talked about the boundary condition 2, which is integration of tau xy dy dot 1. So that is the area minus minus c to c, and this should be equal to your external force, which is, or external shear force, which is equal to P. So what we can do, we can substitute this one. So that will give us 3a c square minus y square dy. You integrate it from minus c to plus c, and this should be equal to P. This implies, so if you take the first term, it is 3ac square dy becomes y, so y, and this goes from minus c to c, right? Then there is minus 3a, y square becomes y cube by 3, and y goes from minus c to c, and this is equal to 0, which implies 3a c square times c minus of minus c, so this will become c plus c, which is 2c, minus 3a y cube by 3, so that is c cube by 3 minus of minus c cube by 3, so this becomes 2 c cube by 3, and this is equal to 0. So if you take it together, this is 6ac cube minus this is not equal to 0, this is equal to p. So minus, this is 3 will cancel out, minus 2a c cube is equal to p, which implies that a is equal to p divided by 4a. A you are calculating, so 4c cube. So a is equal to p by 4c cube. So if you go here and substitute it, what is our sigma xx? Let us see. Sigma xx will become 6 by 4 c cube pxy, right? Which is equal to 3 by 2c cube pxy, right? So now, what is this 3 by 2 c cube? So we were working with this cantilever beam, and this was 2c, right? If you take this cross section, and I said this is 1, so this cross section will look something like this, where this is 2c, this is 1, and what is I for this? bh cube by 12, so 1, 2c cube by 12, this is 8 c cube by 12, which is 2 c cube by 3, which is this one. Therefore, we can write, what should I write? Let me write it here. Sigma xx is actually p xy by I, right? Sigma xx is pxy by I. Now we also have to consider the second term. So let me erase some of the portion and then we will consider. So this boundary condition, it has done its job. You have your A, so you don't need this thing anymore. So then we have this tau xy here. So once you substitute A, what do you get? What is your A? Remember, so A is P by 4CQ. So this becomes 3P by 4CQ C square minus Y square, right? So this P can go inside actually. So we will write it as half 3 by 2 CQ, which will become 1 by I, as you can see, then P C square minus Y square. So this is equal to P by 2I C square minus Y square. So one was P by IXY and another is P by 2I C square minus Y square. So we have sigma xx to be P by IXY and tau xy is equal to P by 2I C square minus Y square, and then sigma yy is equal to 0. You have all your stress components. Strain. Epsilon xx is sigma xx by E minus nu sigma yy by E minus nu sigma zz. Sigma zz is not there. So this is 0. Sigma yy is 0. So epsilon xx is P by EI xy. Right? What will be epsilon yy? Epsilon yy is again minus nu by E sigma xx. The other terms will be 0, which is minus, so nu will be there, and then this thing will come into picture, which is P xy by EI. Right? And lastly, what is gamma xy? Gamma xy is tau xy by G, which is P by 2GI C square minus Y square. One more thing, what is epsilon xy? That is gamma xy by 2. So that will become P by 4GI C square minus Y square. So basically we have computed all the strain components and the stress components. So if you look into here, what we did was we computed all the stress components, this one, and the other is 0, I'm not writing it, and all these three strain components. Okay, this will be epsilon, anyways, this and this. Next step, what is remaining is computing displacement and finding out the displacement of the cantilever beam. Now that we will continue in our next lecture. So I will stop here. This is not complete. We have computed up to the stresses and strains. What is remaining is the displacement, and that we will continue in the next lecture. So I will stop here, and then we will meet again in the next lecture. So thank you.